Foundations of Mathematics for Elementary Teachers. An in-service program designed to provide background for the improvement of instruction in mathematics in the elementary schools. Prepared by E. Glenadine Gibb and Augusta Schurer, members of the Department of Mathematics, State College of Iowa in Cedar Falls. Your instructor, Glenadine Gibb.
Today's discussion assumes an understanding of some of the characteristics and properties of certain geometric figures. Figures such as the line segment, the angle, the simple closed curve, polygon, the cube. Also assumed in this discussion is a knowledge of what we mean when we say that two plane geometric figures are congruent. It is easy to make a comparison between two sets whose elements are discrete. Consider these two sets of pencils. By counting, we can identify the number associated with each of these sets. The whole numbers can be ordered. We can then tell which set has more pencils and how many more. Can we make meaningful comparisons when we are not dealing with sets of discrete elements? For example, let's consider two line segments. It is apparent that we are unable to apply directly the process of counting. We observe that these models are such that they do not have the same length. Is there something that we can count so that we can identify how much longer one is than the other? Let us select a line segment as a unit of measure. And we will then move this measure along this segment. We find 1, 2, 3. The length of this segment is 3 units. We do the same here. 1, 2, 3, 4. We see that this is greater than 4 units, but less than 5 units. In fact, to the nearest unit, we would say the length of this segment is 4 units. Of course, if we would wish to consider fractional parts of this unit or shift to smaller units, we can make a more precise measurement. Returning to this segment, we could describe this by saying that the measure in the unit that we've used here is 3, or that this segment has a length of 3 units. We observe that basic to a discussion on the measurement of line segments is the idea of comparison between a line segment and a unit segment. Let us consider other line segments. We can make a model tracing of line segment AB and observe that line segment AB is congruent to line segment EF. We can record that by writing that segment AB is congruent to segment EF. But what is the length of AB? Let us select this as our unit. We see that the length of segment AB is 3. We can record that by saying that the measure of AB is 3. We find the length of EF. We see it is also 3. we record it. We can also write then that the measure of segment AB is equal to the measure of segment EF. What is the measure of CD? Using our segment again, we see that this segment has a length of 4 units. We record this. We observe that the measure of CD is greater than the measure of AB, or we can write the measure of CD is greater than the measure of AB. Once we have chosen a unit, every line segment has an exact measure. These measures then allow us to compare the lengths of line segments. But let's consider now the union of line segment AB and CD. If we were to consider the number associated with the union of our 2 sets of pencils, we would find the sum of the numbers associated with each of the sets. The measure associated with the union of segment AB and CD is found by adding the measure of each of the segments, or 3 plus 4 is equal to 7. Although we can arbitrarily assign a measure, it's acceptable to use standard units for purposes of communication. Some of the standard units used for linear measurement are the inch, the foot, the yard. An appropriate measure is selected according to that which is to be measured. For example, the inch. It is suitable for measuring along the edge of a picture. A yard would be suitable for determining the width of a classroom. Once a unit is selected, the creation of a scale simplifies measurements. We can use a straight edge and mark off on that a unit of our selection. As in doing so, we are making a ruler. Once the unit has been selected, every line segment has an exact measure. However, all measurements made in the physical world are approximate. They are dependent upon the precision of our scale and the care exercised in making the comparison. Let us now consider mark AB, a model of line segment AB. Suppose that we select this as our unit and then have made a scale. What is the length of this mark? We see that it is greater than 4 units, but less than 5. To the nearest unit, and if this was the best scale we had, we would say then with this unit that the measure is 5. We can record that in this way. Reading this recording, we would understand that the mark is somewhere between 4 1/2 units and 5 1/2. But now let's consider another scale. This time we'll take one which is marked in half units. as we have here. Again, we find the length of our mark, and we see that this is greater than 4.5, but less than 5. Using this half-unit scale, then, we would write that our measure is of AB is equal to 4 1/2. Reading this measure, we would understand then that the mark is greater than 4 1/4, but less than 4 3/4. If we were to read this, thinking of this scale, would say to us that our mark is greater than 4 3/4, but less than 5 1/4. We could use still other smaller scale divisions, and we can make a more precise measurement. The segment AB has an exact measure. However, using any of our rulers, we obtain an approximation of that measure. The smaller the divisions on the scale that we use, the more precise our measurements will be. However, if the scale is read carefully, the measurement of our mark should be in error by no more than 1/2 of the smallest scale division. A familiar application of linear measure is that of finding the length or perimeter of a polygon. Consider this model. Using the same unit of measure and then knowing the measures of each of the sides, we can simply find the perimeter by finding the sum of those measures of 3, 6, 5, 9, 4. This polygon has a perimeter of 27 units. Suppose that we considered a simple closed curve such as this. It may be not as easy to find the perimeter. One way that we could do it would be to place a string on the simple closed curve, much in this way, and then finding the length of the string. But let's consider some other measurements of geometric figures. You recall that we can make comparisons of angles to find whether or not they are congruent, or if one may be larger than the other. But we ask, how much larger? We select a unit angle, and we find then that the measure of this angle is 3 using this unit. We can record that in this way. Now, once we have decided or selected a unit, we can make a scale for measuring angles, much as we made a scale ruler for measuring line segments. Such a scale for measuring angles is known as the protractor. Here again we see our measurement. Measure 3, and for this angle, the measure 5, and we record it. Again, precision of measurement is controlled by the smallest subunit indicated on our scale. We have seen how we can assign measures to line segments using unit segments, measures to angles using unit angles. Let's see how we can assign measures to regions using unit regions. consider this plane region. We select a unit of area. Suppose we select one like this. We then see how many of these units it takes to cover this region. We have 2, 4, 6, 8. Using this unit, this region has an area of 8 units. But we could consider another unit region. This time, we take one, such as this. Again, we cover the region. This region has an area of 4 units. Let's consider still another unit region. This time we will take a circular region. Again, we cover the region. We know that the area must be greater than 8 of these units, for all of the region hasn't been covered. We can consider still another unit, this time a square region. Again, we cover the region. Using this unit, the measure of the region is 8. Some of the standard units that we use to measure regions include the square inch, the square foot. But now, consider this region. You will recall that when we made an approximation of the length of a line segment, we used a ruler. Let's use a grid made up of unit regions of area to approximate the area of this region. We find that we want to identify all the unit regions that lie completely inside our simple closed curve. If we count these, we would find that we have 21 such units. Now, let's find out how many unit regions it will take to completely cover this region bounded by this curve. This time, we need to include these. If we count these, we will find that it takes 41 unit regions. We can make an estimate of the area of this region. We say that it's between 21 and 41 of our units. Of course, a finer grid would give us a more precise measure of the area. Sometimes we can use linear measure to find area. Consider this rectangular region. We can use a grid again and see that we have 6 of our units, 4 rows, or that we have 6 times 4 units of area. We can express that also in this way, of using the idea of ratio, that we have 6 units in 1 row, and so in 4 rows we would have n, or in this case, 24. But we see here that the measure in this unit this side of our rectangle is 6. The measure of this side is 4. The product of those two measures would then identify the area of this rectangular region. We use our formula saying that the measure of the area can be determined by the product of the measure of the base and the measure of the height. We can use our methods of finding areas of rectangular regions to find areas of triangular regions and other regions such as those that might be associated with a parallelogram. Let's look at some of these. First, we'll consider the triangular region. Think of another region congruent to this triangle. And think of the vertex. And from that vertex, a line segment perpendicular to the opposite side. We call this line segment an altitude of the triangle. Think of cutting along that line. We can then build a rectangular region whose measure of the base is the same as the measure of the base of the triangle, and whose measure of height is the same as the measure of the altitude of the triangle. The product of these two measures would then give us the product of the area of the rectangular region. Dividing by 2 would give us the area of the triangular region. Or we can say the measure of the base times the measure of the altitude divided by 2 is equal to the measure of the area of our triangular region. But consider still another model. This time, let's think of the altitude again. And then let's think of folding this model so that the vertex of the altitude coincides with the intersection on the opposite side. Think of cutting along this line. Think again of cutting along this line. Again, we build a rectangular region. A rectangular region whose base is the same as the base of the triangle, whose height is 1/2 the altitude. Using this model, the measure of the triangular region then can be determined by the measure of the base times the measure of 1/2 the altitude. Consider a region associated with a parallelogram. Think of another region congruent to that. Now think of a line perpendicular from one side to the opposite side. This we can call the altitude of the parallelogram. Think of folding and cutting along that line. We build a rectangular region, a region whose base is equivalent to that of the parallelogram, whose height is equal to the height or altitude of the parallelogram. We see then we can find the area of a parallelogram by finding the product of the measure of one side and the measure of the altitude perpendicular to that side and the opposite. We can use our ways of comparing line segments and plane regions to extend to think about comparing space regions. For example, we look at two space regions such as we have represented here. How can we tell which has the greater volume? Of course, we could pack one and then pour the contents of that into the other container, and we pack that. We see, much as we try to pack in, that this container does not hold as much as does this. We could say that this has greater volume, but we ask, how much greater? We need to select a unit of volume. It may be represented by a ball or a block. We can use those units then to pack into our regions of space. As we look at these, we see that the blocks pack better than do the balls. This would indicate to us that a cubic block is a much better unit for volume than a spherical one. Some of our standard units for finding the measure of volume are the cubic inch and the cubic foot. We've indicated some ways of associating numbers with line segments, with plane regions, and with regions in space. We've seen how we can use those numbers or measures for making comparisons. There are, of course, no line segments, triangles, or cubes in the physical world. We can make use of our theory of measurement as we've developed it to assign measures to models of line segments, to models of plane regions, to models of space regions. However, we must remember that all these measurements are approximate. They are dependent upon the precision of the scale we use and the care exercised in making the measurement. In fact, the standard units, the inch, the yard, that are used to make the scale are themselves only approximations.
Foundations of Mathematics for Elementary Teachers has been presented by State College of Iowa under a grant from the National Science Foundation and prepared by E. Glenadine Gibb and Augusta Schurer, assisted by E.W. Hamilton and Diane Baum. The program was produced and directed by Robert Gabler and recorded at KDPS in Des Moines, Iowa.